In Lesson 6.1, Area of a Region Between Two Curves, we'll further explore the applications of integration after having gone through Chapter 5, where we learned all kinds of difficult integrals and how to evaluate them. Here, we're just dealing with applications in Chapter 6. In Lesson 6.1, we'll build upon the idea of the integral as an area. Previously, we did this, but we only looked at the area between the x-axis and some given function. Here in 6.1, we'll look at the area between two given curves, regardless of where the x-axis lies. Further on in Chapter 2, we'll take a look at volumes of surfaces of revolution, and then conclude Chapter 6 by looking at arc length and surface area of these volumes. So, with all that being said, let's go ahead and keep it simple and just take a look at area. Here in Lesson 6.1, we'll begin by taking a look at a formula that we can use to help us evaluate areas of these regions. Let's take a look at that formula right now. So, although the concept of finding an area between two curves is relatively easy, I'm still going to give you a formula to be able to tackle some of the more difficult problems. But before I give you that formula, let me go ahead and draw a picture of exactly what's happening here. What we want to do is, given that I have two functions, let me call this one f of x, and let me draw another one that I'm going to call g of x. If I want to find the region that is between these two curves, in this situation, this region here, let's say, all I really need to do is find the x values of their intersection, and I'm going to call those a and b. And all that being said, all I really need to do to find the area is to evaluate an integral that goes from a to b of f of x minus g of x. That's really all there is to it. Essentially, what's going on is we're finding the area under the curve f of x, and that does need to be the higher of the two. So I'll put a caveat here that f of x must be greater than or equal to g of x for all x in the region that I'm looking at. So what this does is it finds the area under the curve f of x, and then it simply subtracts the area under the curve of g of x. So although I am finding the area between two curves, the way I'm really doing it is finding the area under the top curve and subtracting the area under the bottom curve. And what I'm left with is this area in between the two curves. So what would happen if the curves do overlap a number of times? In other words, what if I wanted to find both of these areas? Well, to do that, I would have to have two integrals to evaluate, and that's simply because in the area formula, the first function must be always greater than the second function. So this would just require two separate integrals, one for the first area and one for the second. No big deal. Anyway, all this being said, let's go ahead and see how this works in action, and we'll begin with example A. In example A, we're asked to sketch the region represented by this integral right here, and then find the area of that region. Now, of course, what I've done here is not actually graphed the integral as you see it, but rather graphed the two functions as they exist in the integral. What I'm referring to, of course, is the first function right here, which is graphed in red. I'm going to call this function f of x, and that is, again, the function that's graphed in red. And then secondly, I'm going to graph this function, x over 3, which is, of course, a linear function, and that is this function that's graphed in blue. Now, if I'm going to sketch the region represented by this integral, then I'm only looking at the area between these two curves, between the x values of 2 and 3. So I've already gone ahead and drawn vertical lines here. And essentially what we're going to be doing is finding the area under this red curve all the way down to the x-axis. So our first part of the integral will find this red area. Once we've done that, we can go back and subtract the integral of this blue function right here, and the blue function has the area represented down here. So if I find this red region and subtract this blue region, of course what I'll be left with is the area between x equals 2 and x equals 3, between the red and blue curves, and that is the black region right here. So it might take a while to get used to what's actually going on. But as far as the calculus goes, that's not too bad. If I want to go ahead and integrate this integral, it might behoove me to actually simplify this integral first, rather simplify the integrand. And if I do that, I'm going to have x cubed over 3 minus 4x over 3. And I just did that by combining like terms, of course. Well, if we go ahead and integrate that integral, it won't be too bad. Simply x to the 4th over 12 minus 2x squared over 3. And again, we'll evaluate that between x is 2 and x is 3. So if we evaluate this whole thing when x is 3, what we're going to end up with is 81/12 minus 18/3, which, yes, you can reduce, and we'll do that in just a moment. And when you plug the 2 into both of these, what we'll end up with is 16/12 minus 8/3. So great. If we go ahead and simplify all that down, what we'll end up with is 25/12, and that is the area of the region here in black. So there's the area between two curves. That's how it's done, both the concept and the execution of these types of problems. So all that being done, let's go ahead and take a look at 6 more examples. That'll be fun and exciting, and it will definitely drive the point home as to how to find the area of a region represented between two curves. Let's go ahead and take a look at example B. So here in example B, once again, we're given 2 functions, and we need to find the area of the region between these 2 functions. Once again, that's this area here in black. So in order to do this, we first need to find our bounds of integration. Where does this area begin, and where does this area end? Based on this graph, it might be easy to tell that this does start when x equals 0, and it appears that this area will conclude when x equals 3. Sometimes it's easy to tell on the graph, but remember, of course, if we cannot tell, then what you'll need to do is actually set f of x equal to g of x, and then just actually solve for the 1 or 2 values of x, and those will be your bounds. So in this particular case, we can tell graphically, so we really didn't have to worry about too much. Also in this example, it's pretty easy to tell which function is on top over the entire interval representing this region, but anytime you can't tell, it's always a good idea to draw a representative rectangle, simply a rectangle that goes from the top to the bottom of the region. This is very similar to some things that we've done earlier when we were evaluating area, but when you do that, you'll then be able to tell which function is higher and which function is lower, just in case you need to stack your integral correctly. So anyway, now that we know this, we see that we're going to be integrating between 0 and 3, and we can simply tell that the quadratic equation is the one that's on top, if you will. So I'll simply do f minus g for this interval, and I'll actually write this here, f minus g, and I'm just going to go ahead and skip a step and just go ahead and subtract them right off the bat. If I do that, I'll have negative x squared plus 3x dx. What happened to the 2? Well, of course, the 2 canceled out with this 2 over here, and this 3 simply came from this 4 minus this 1. So there we go. It's a pretty simple integral to evaluate. If we do this, we should, of course, get negative x cubed over 3 plus 3x squared over 2. And if we evaluate that from 0 to 3, I'm going to skip all the steps, but if I did it correctly, what we will get is 9/2 as the area of this black region. So you can see that we do need to find the bounds of integration, and we do need to determine which function is the higher and which function is the lower. Oftentimes it's easy to do, but if ever you run into trouble, just consider drawing a representative rectangle, and it will show you the top and bottom. Solve the 2 functions for each other, and you'll find the bounds of integration, which we refer to as A and B in the area formula. So there you go. We're going to move on to example B, which is or rather C. It is a little bit different because it is functions in terms of y rather than in terms of x. But go ahead and try the problem before we get there together, see how you do, and then let's proceed on to example C. So in a fun and exciting twist, here in example C, we've established two functions that are both functions of y in order to find the area of the region between these curves. If you take a look at these two graphs, which might take you a second to do, but of course I have some computer software to do it for me. However, if we were to find the area, if you were to draw a representative rectangle here, you would notice that at times the red function is at top and the blue function on bottom, but at other times, such as over here, we run into more difficult matters where the red function is both the top and the bottom. Well, that is a problem. Fortunately, since everything is a function of y now, we can draw different representative rectangles. What I'm actually going to do is draw a representative rectangle that is horizontal this time around. And if we do that, rather than saying which function is on top and which function is on bottom, what we can simply talk about is which function is greater versus which function is less. And if we do that here, we can see that the red function is the greater function, while the blue function is the less one. So rather than top or bottom, we're now dealing with right and left. Regardless, either way, it's which function is greater and which function is less. So all this being done, let's see what this integral would look like. Well, we're going to integrate from where to where. Of course, because our rectangles are horizontal now, we're not looking for x bounds. We're actually going to be looking for y bounds. So here we're going to have where y is 0, and it appears on top we will have where y is 3. So those will be our bounds of integration, 0 to 3, but not on the x's, but on the y's. So be very careful there. What we are going to have is the quadratic function being first, since it is the greater function. That is the y quantity 2 minus y. And then we'll just subtract the blue function, which is the lesser of the two functions. This time, instead of being dx, it'll be dy. So if we go ahead and simplify this integral down just a little bit, what we'll actually end up with is going to be 3y minus y squared dy. And again, this is not a very difficult integral to deal with. This will simply be, let's see here, 3y squared over 2 minus y cubed over 3. That evaluation of the integral might look familiar to you. I feel like we've recently done an integral with that exact same evaluation. And in fact, if we plug in our values, we'll see a lot of more commonalities. And our final commonality is that our area here is going to be 9/2. Again, that is the area of this region that I'm coloring here in black. You might say to yourself, well, that looks a lot like the region from our previous example, example B. And if you say that, you are correct. This is simply a rotated copy of example B. So, of course, it would have the same area. And there you go. I'm just glad that we got to see what happens when we have horizontal rectangles rather than vertical ones. So there you go. Unfortunately, the rest of our examples will all be vertical, although in your 6.1 assignment, be on the lookout for horizontal rectangles. When that happens, remember that your bounds will be y bounds rather than x bounds. Be very careful. And now, let's take a look at example D. In example D, we're going to try to find the area between this given function f of x, which is here in red, and this blue function, which is actually just the function y equals 0. That being said, we really are just finding the area under the red function to the x-axis. And although that is something we have done before, we haven't quite done it this way because this particular integral we would not have been able to evaluate prior to Chapter 5. If you take a look at it, you'll see what I mean. Anyhow, we are going to evaluate this integral between x equals 0 and x equals 3. And so it is this, once again, this black region that we're going to try to find the area of. Now, this isn't a particularly difficult problem necessarily. It's just that the integral is relatively new, something that we just learned in the most recent chapter. And so, if we want to go ahead and evaluate this, we're given that our bounds are 0 and 3. Our upper function, or greater function if you will, is going to be 6x divided by x squared plus 1. and I'm going to subtract our lower function, which is actually just 0. So I'm not even going to bother subtracting 0. We're just going to find the integral of this function between 0 and 3. Now, this is not a simple function to do. It's not difficult, but it's not simple. In this particular function, what I'm going to do is let u equal the denominator, that is x squared plus 1, and then du will simply be 2x dx. Now, in order to get there to be a 2 in the numerator, I am going to have to play around with this just a little bit. So let's see. If I want a 2x up there in the numerator, what part of this function am I missing? And you might realize that in order to restore it back to its original form, I simply need to multiply it by the constant 3. And so that constant I'll put outside. And now I can go ahead and take a look at this as 3 times the integral of du over u. And of course, we should be very familiar with what that is. That's simply going to be the natural log of the function u, which in this case is x squared plus 1. Now, if we evaluate that between 0 and 3, what we're going to end up with is 3 multiplied by the natural log of 10 minus the natural log of, well, 1. And of course, the natural log of 1, we all know that that is just equal to 0. And that means the area of this black region is simply going to be 3 times the natural log of 10. As a decimal approximation, that is equal to approximately 6.907. And that is the area of that black region. So, although the concept is not very difficult, the actual calculus of it could require some advanced capabilities. Fortunately, we've made it through Chapter 5, where we learned all about the natural log and its derivative and all that good stuff. So, there we go. And with that, let's go ahead and take a look at a trigonometric version of an area of a region. This will be a lot of fun here, and this will be example E. I hope trigonometry doesn't scare you, because here in example E, we're going to look for the area of a region bounded by 2 trigonometric functions. It shouldn't make any difference as far as the integral or the math goes. Conceptually, everything is still the same, but it is trig, so we will have to deal with that. I've gone ahead and graphed both the functions here on this graph. And what I need to let you know is that the first function, which, again, I've graphed in red, is actually this time the less than function, if you will. We need to recall that when we're setting up the integral, the less than function actually comes second. And the second function, the cosine of 2x, I've graphed here in blue, and now that's actually going to be our greater than function. So we need to be very careful. Now, we're still finding the area between the two graphs, and that's the area here in black. But the only concern we really have is the order that we place these functions in the integral. Well, there is one other concern, actually. You might be worried that part of this region is below the x-axis. Is that going to cause problems? Well, actually, it won't. Because we're subtracting these two functions, anything that is negative along the interval will actually become positive because of the subtraction. So really, we have nothing to worry about at all. So that being said, let's go ahead and set up our integral. We're told that our two bounds are negative pi over 2 and positive pi over 6. And as we discussed, the blue function is actually going to come first this time around. So we'll have the cosine of 2x subtracted by the sine of x dx. Now, I'm not going to go through the whole rigmarole of integrating this thing. You should be very familiar with doing that on your own by now. And what I'm actually going to do is integrate this as two separate integrals, once for the cosine of 2x and then once for the sine of x. Doing that should not be a big problem. If I integrate the cosine of 2x, what I'm actually going to end up with is 1/2 times the sine of 2x. And I'll evaluate that from negative pi over 2 up to pi over 6. And then I'll simply subtract the integral of sine x. And what is the integral of sine x? Well, that's, of course, going to be negative cosine x. So that'll make this go positive. I'll have cosine x, and again, from negative pi over 2 up to pi over 6. So if we go ahead and plug some things in here and do some fundamental theorem of calculus, what we'll end up with is 1/2. Well, when I plug pi over 6 in here, what I'm actually going to end up with is the sine of pi over 3. Sine of pi over 3 is, of course, square root of 3 over 2. And when I plug in negative pi over 2, that'll be the sine of negative pi. That is just 0. So there it is for the first part of our integral. For the second part of our integral, we're going to plug these into the cosine of x, and let's see what happens there. Well, the cosine of pi over 6, that again is just square root of 3 over 2. And the cosine of negative pi over 2, well, that's just going to be 0. And so if we work all this out, looks like we're going to end up with the square root of 3 over 4 plus the square root of 3 over 2. And that, of course, is just going to give us 3 square roots of 3 over 4. Now, numerically speaking, that is approximately equal to 1.299. And that is the area of that black region. Feel free to try running this through your calculator without doing any of the calculus by hand. See what the calculator gives you. It should tell you 1.299. And so there you go. Even though we're using trig, the concepts, the math, the idea, all of it is really still all the same. So good stuff. All right, well, let's take a look at one more normal example, if you will. Example E, where we're again going to have to try something that we wouldn't have known to do prior to Chapter 5. Let's go ahead and take a look now. So in example F, we're again given one of those functions that we want to find the area under all the way down to the x-axis, because our second function is y equals 0. So here is the graph of g of x equals 4 natural log of x over x, and the graph of y equals 0. We're told that we want to find the area of the region between those two graphs, which clearly intersect at 1. And then we want to go up to where x equals 5. So that's going to be about right here. So you can see the region that we're wanting to find the area of. It's mostly rectangular in nature, although it is a little bit curved. So unfortunately, we're not able to use a rectangle formula. But that's all good. We know how to find areas of regions now simply by finding the integral of the greater function minus the lesser function. So let's go ahead and set this integral up. Setting it up is not going to be a large chore. We're simply going to go from 1 to 5 as specified both by the graph and by the problem itself, from 1 to 5. The 4 on g of x, I'm actually going to move out front because it's a constant. And so we have the natural log of x divided by x minus the second function, which is just 0. So again, I'll leave that out. And there is my dx. Remember, again, I haven't mentioned it yet this lesson, but remember that this, the function, is actually representing the height. When I'm subtracting functions, it's still representing the height of a representative rectangle if I were to draw one. So that is the height of the rectangle, but don't forget that the dx that is represented in every function that we've done here, in every integral, dx or dy if you will, is actually representing the width of the rectangle. So we really are still just finding areas of rectangles is all we're doing. Anyhow, in this case, there is no simple formula for the integral of natural log of x over x, so it might require some u du substitution. Hopefully that wouldn't be too difficult here. I can see that if u is the natural log of x, then du would simply be dx over x, and that's exactly what I have right here. So really, this integral is going to turn into 4 times the integral of du over u. Or rather, I apologize, it's actually going to be u du as such. And so there we go. That should be a very, very easy integral to evaluate. We're simply going to get u squared over 2. And when I turn that back into its x form, the 2 and the 4 are going to interact in such a way that I'm just left with 2. U is going to be, or rather u squared is going to be the natural log of x to the second power, and we're going to evaluate this again from 1 to 5. So evaluating this from 1 to 5, I have 2 natural log of 5 to the second power minus the natural log of 1 to the second power, and of course that's simply going to give me 2 times the natural log of 5 squared, in that the natural log of 1 is actually just 0. So there we go. There's no more simplification I can do to this. This is, in fact, the area of that black region. And again, if I want to approximate it in a decimal, I'll get about 5.181. And that is going to be the area of that black region. But again, don't forget the concept of this. The function, or the subtraction of functions, is simply the height of the rectangle that I'm drawing, while the dx or dy is quite simply the width of the rectangle. So the integral is, of course, adding up all those rectangles along the interval, giving me, of course, the area of that region. So we've done countless examples now finding the areas of regions. Let's round this out with one more example dealing with an accumulation function so that we can find the area of any region from a point up to any value of x that I choose. This is going to be a good example. Try to wrap your head around example G. So here in our last example, example G, we're going to try to find this accumulation function given this integral. Now, I'm going a little bit backwards here. I've actually graphed the integral already, 1/2 t squared plus 2, and it does make this parabola. Of course it does. It's a quadratic equation. But if we want to find the area under this parabola between 0 and any value of x, we will need to integrate this quadratic function in order to come up with an elementary algebraic function to which we can just plug in various values of x. After we do that, we'll actually evaluate this for capital F of 4 and capital F of 6. Now, where does the region begin? Well, if you look at this integral, clearly it begins at x is 0 and proceeds up to whatever value of x we plug in, which is why we're treating that upper bound as a variable. Well, let's just go ahead and evaluate this integral right off the bat. It should not be very difficult at all. Of course, the integral of 1/2 t squared is simply going to be t cubed over 6, and the integral of 2 will simply be 2t. Now, once again, we're evaluating this between 0 and x, meaning that our accumulation function is actually just going to be x cubed over 6 plus 2x. When I plug in the zeros, they both won't equal anything, so I can just leave it as this. Now, this will evaluate the area of any region here that begins at 0 and proceeds up to the value of x. So if we want to find capital F of 4, let's first draw what that region looks like. It's going to start at 0 and go up to 4, which is right here. So what we're about to do is find the area of this red region. Now, I'm not as good at coloring these in as I wish I were, but our region is going to look something like this, and all I need to do is plug 4 into our accumulation function, and it will tell us the area of this region. So go ahead, plug 4 in here. What do you get? When I did it earlier, what I ended up with was about 56 thirds. And hopefully you end up with about that same thing. 56 thirds is approximately equal to 18.666 or so. And that's going to be the area of this red region. Now, let's try this one more time, but this time, let's go up to F of 6. This will be the region starting at x is 0 and proceeding up to this vertical blue line. So this time we're going to find this region. Now, I'm not going to color the whole thing in because that seems to take too long. But if we want to find that blue region, just go ahead and plug 6 into our accumulation function. And if you get the same thing I got, it's just going to be 48. And you might say to yourself, wow, 48, that's a whole lot bigger than 18.666. And you're right, but look at all the extra space that we've added. And so it does kind of make sense. In fact, if we were to subtract these two values, what we would find is the area of just this extra region right here. So that could be interesting to do, although it is beyond the scope of this particular problem. So, there you go. Good stuff. And so, here in lesson 6.1, our main focus has been finding the areas of these regions that are often bounded above or below or even to the left and to the right by two given functions. Now, sometimes that function is just x equals 0 or y equals 0, in which case there's not a whole lot new to this concept. But in a general case, finding the area of the region between two functions involves setting up a number of representative rectangles. The height of those rectangles is simply the subtraction of the two given functions. And the width of the rectangle, well, that's just d of x. Of course, sometimes we have horizontal rectangles, and in that case, the height, you can call it the width if you like, is just the subtraction of the functions, and the height, or what we could call the width, is just dy. Regardless, it works out the same way. We subtract the functions in the integral, and we put a dx or dy with it. But remember, it's always the greater function minus the lesser function. Greater minus lesser. That could mean top minus bottom. It could mean right minus left. But it's always greater minus lesser. Now, the only trick to this sometimes is finding the bounds of this region. If the region we're looking for is the region that's enclosed by the two functions, then we do need to find out where the two functions intersect. That could help by, or we could do that by graphing the two functions, and sometimes we can eyeball where they intersect. But when not, what we can do is use algebra to set the two functions equal to each other and solve. Sometimes we can just use brute force and just come out with their x value of intersection. Or, quite honestly, if you're allowed to use your calculator, you could just use the intersect function into your calculator. If you don't know about the intersect function, of course, I strongly encourage you to look that up. It's very, very helpful to know about that. All right, so finding the areas of regions, conceptually not difficult. Mathematically, sometimes easy, sometimes hard. Just depends on the functions that they give you. But remember, it's always greater minus lesser from the lower bound to the upper bound. And there you go. So remember all this as you're working on your 6.1 assignment. And good luck.